that remember me from Waterloo and my LaTeX skills might not be surprised if I tell you that the creation of these slides has involved several more people. So, all right. I'll get going with some very basic stuff. First, what is an arborescence? Well, an arborescence is a digraph. And the underlying graph of that digraph is always a tree. And I fix a root in that tree, and I say all arcs are rooted away from that root. Or equivalently, I can say in that orientation of the tree, the root has in degree 0, and all other vertices have in degree 1. So, for example, what you see here on the left is an arborescence. I have this vertex R, everyone's oriented away from it. And what we see here on the right is just whatever. So that's not an arborescence. There are several vertices that have in degree higher than 1. But this is just an orientation of a tree. This is not at all an arborescence. These are the things that I call arborescences. Okay. A few more basic definitions. Usually, I don't want to look at an arborescence as such, as an isolated graph. I want to find arborescences in a given graph. So, for example, if the whole graph here is a digraph, is the digraph D, and the green one is the arborescence. That's the arborescence in a graph. And now, what's important is when I mean an arborescence spans certain vertices. This is just the vertices which are part of that of the digraph. Okay. And an arborescence is spanning. So as a global attribute in the whole graph, an arborescence is spanning if it spans all the vertices in the graph. So that is a spanning arborescence. It spans these 3 vertices, and they are actually all the vertices in the graph. Okay. Now, one question on arborescences is, when can I have several disjoint arborescences in a graph? And the starting point of all our research is the following theorem of Edmonds, which characterizes graphs which have at least k disjoint arborescences with the same root for a given constant. And this says I have k disjoint arborescences if and only if every subset which does not contain R, subset of the vertices, has at least k incoming arcs. So if I look at that here, that is what I want. When I have k equals 2, I have fixed my vertex R. I want 2 arc disjoint arborescences which are spanning the green one and the violet one. And the condition is that here. I have, for every set X that does not contain R, I need at least 2 arcs coming in. That can easily be seen because every vertex has to span the vertices, every arborescence has to span the vertices in X. And the arborescence starts outside, so it has to come in some way. So I need at least 1 arc entering for every arborescence. Okay. Now I will show you a first slight strengthening of that theorem. This says, again, I want to have my k arborescences, but now I don't want to have the same root for all of these arborescences. I want that I can assign arbitrary roots to these arborescences. And I do not mean that the arborescences can have arbitrary roots, but I fix the roots. And after that, I say I want to have the arborescences so that they have exactly these roots. And there's that characterization. Again, we can easily see that this condition is necessary because if I have given a vertex at X, every arborescence either has to start in X or has to get into X. All that do not start in X have to get into it. And now I will for the first time show you a thing that very often happens in these kind of settings, that you can conclude one theorem from the other one. And in that case, this is pretty simple. I just add one vertex, which is my new root R, and I add one arc from it to every designated root. And now basically the vertices I desire to have in the smaller graph, that's exactly the same than if I want to have my k-spanning arborescences from R in the new graph. So what I can do is I can just apply the theorem, the first theorem of Edmonds to that graph. And that gives me that theorem here. Okay. Now, for my purposes, I like to think of these arborescence packings in a slightly different way. I like to have a kind of separation between the roots where the vertices started, and where the arborescences start, and the vertices I want to span. So therefore I need this definition of a first definition of a root. So now root does not mean an arborescence in a root anymore, but I look at the whole graph. And now this is a global property for the whole graph. A vertex is called a root if there's no one coming in. And further, I call a simple root if there's only one guy coming out. So this is at most one, but actually we can think about exactly one because isolated vertices are really not interesting in that setting. Okay. And now the objects I consider I will call rooted graphs or simply rooted graphs. But this is where I have, as I said, I have separated the vertices and the roots. And this is just a digraph. And these two sets are separated in some way. And all the sets of R, all the vertices in R are roots. And if they're all simple roots, then it's a simply rooted digraph. Okay, so that all clear? I hope, by the way, we are so few people, you can always interrupt me if you have any question. Okay. So now I can restate the second theorem of Edmonds. And I was restated in the following way. Now what I do is for every root I have, so for every arborescence I have, I add a root, and I add an arc from that root to where the original arborescence was supposed to start. Or vice versa, if I have that if I have that setting, I can take away my roots and I say you start at the only out neighbor. So this is actually a restatement of the theorem I showed you 2 slides before, that one. Okay. Now, what I will need today and what will play a decisive role is a slightly stronger theorem of Edmonds. It looks almost the same, but nevertheless, it is quite different. It is much harder to prove, and it is really, really stronger. And it will look almost the same, with the only difference that this word simply will be deleted. That's the same theorem. You want the same thing, you get the same conclusion, but you're in a slightly more general setting. So now what I allow is that immediately out of the root vertex R, I have several arcs coming out which belong to the arborescence. So we will use this theorem, and I remark again, its proof is way more complicated than the first theorem. Okay. Now, there is one thing that is maybe not so well covered by Edmonds' theorem. This is the question, what happens if a certain vertex in V is not reachable from some root vertex R? For example, if I look at that graph, then this vertex V is not reachable from R. Well, what does Edmonds' theorem tell me now? Well, it just tells me you can't find the spanning arborescences. Well, of course you can't. You have this vertex R, and you can't ever have an arborescence that reaches V. So of course you can't find your spanning arborescence packing. So, but anyway, I might say this graph still looks pretty well connected to me. Can I not say something weaker? Can I say at least I want to have a packing of arborescences, each of which spans the vertices it can reach? So for example, this is what I call a reachability arborescence. I pick that root. I look at all the vertices which are reachable in the original graph from the root, and I search for an arborescence that spans them. For example, for this root R, I can reach the two red vertices. And so this thing I marked in green is a reachability arborescence for that root. And now when I speak about reachability arborescence packing, then I look at all the vertices, when I speak about the reachability arborescence packing, I mean that all the roots have a reachability arborescence and the arc disjoint, and of course the vertices which are reachable are not the same for all roots. So the root on the left can see all three vertices in V, and the root on the right can only see these two vertices. Okay, and we want to pack those, and I want to show you a theorem on that, and for that I need one little definition. Namely, if I pick a vertex set in the graph, by PDX, I mean all the sets which are in that root set and from which X is reachable. So for example, if I pick one of the two vertices on the right, PDX, if I pick, say, a set, an arbitrary set basically, that contains one of the two vertices in V on the right, then this will contain, PDX will be both the root vertices, and if I only pick the vertex on the left, then this will be only the root vertex on the left. Okay, so now I can tell you the theorem, and this was proven by Kamiyama, Kato, and Takisawa in 2009. And okay, so I kick off again with that root digraph, and I say I want now I'm packing of reachability arborescences. And I can get this if and only if the indegree of every set X, that's in V union R, is at least that term here. And again, this is rather simple to see. I look at X, I know exactly the roots in PDX need to see X. Every arborescence that has a root in PDX needs to come into X. So I have the roots that already start in X, and all the rest has to come in. So again, you can easily see that this is necessary. But of course, proving sufficiency is less trivial. Okay. So now I want to talk to you about how to prove this theorem. So the original proof of Kamiyama, Kato, and Takisawa was based on they did some submodular arguments, and it is not quite easy. It is certainly a very good article, but it's somewhat more technical. And there's a somewhat simpler proof can be found in the book of Frank, but it still uses a lot of submodular ideas. It's still not quite easy. And okay, and so what we want to show you is an inductive proof of this theorem. Basically, the only thing I want to use is the strong theorem of Edmonds on spanning arborescences, which I showed you before. And the inductive proof should be self-contained otherwise. Okay, so I will jump right into the proof. As I told you, it is an inductive proof. So we will start with a minimum counterexample. Okay, so I know this graph does not have the Syod packing, all smaller graphs do. And now what I want to find first is a strongly connected component in the upper part in V, which has no arc leaving. Okay, why does that exist? Well, V itself has no arc leaving by construction, because all these are roots. All vertices in R are roots. So by definition, there is no arc leaving V. And now I can just look at the strongly connected components of V. And of course, there is one that has no arc leaving, because otherwise I would get a contradiction with them being strongly connected components. I would get a cycle in some way. So, okay. I want to apply induction, and what I want to do is I want to first take away that strongly connected component. So that's what I'm left with. But what do I know? I can now take an arbitrary set, vertex sets in the graph that's left. What I can see is that because no arc came out of C, that the indegree of an arbitrary set in the vertex set of the graph that's left has not changed. I can't have taken away any in neighbor because C had no out neighbors. And in the same way, I can also see that the vertices from which that set X is reachable is the same, no matter if C is in the graph or if C is not in the graph, because C has no outgoing arcs. Okay, and so now I can apply induction. Because, of course, D minus C is a smaller graph, I have taken away C. So now I get my reachability packings, reachability arborescences. So basically, this is all I want. This is all I want from my induction. I've taken away a strongly connected component. I can apply induction, and I do so. Okay. Now, in some way, I have to consider the rest. I have to see how to extend these arborescences to the strongly connected component C. Okay. And for that, we need a little construction. We've constructed a digraph. Okay. In that digraph, I want to apply Edmonds' strong theorem to get spanning arborescences. And then I want these two arborescences to be created in a way that I can merge them with the arborescences before. Okay. So what will my digraph D prime look like? Well, I mean, I'm searching for packings in C, so certainly C should in some way be contained in that digraph. Further, I need in some way to use the arcs that enter C. They need in some way to be in the arborescence. I need these arborescences to enter C in some way. So I really have to consider the arcs that enter that set. Therefore, what I do, for every arc that enters C, I create a new vertex. So for example, there's that arc here that enters C, that's for that vertex. Okay. And from each of these artificial vertices, I make an arc to the head of the corresponding arc in the original graph. Okay. Now I also need to consider roots. I need to know for which arborescences can I possibly use the arcs that enter C. So in some way I need to contain the roots in my graph. But I do not actually need all of the roots. The only roots I need are those that can actually see that strongly connected component. And I will call them R prime. So in my example, it's the same roots. But if you have an example where there is some root from which no vertex in C is reachable, then I will not use these roots in that graph. Okay. Now, when can I use an entering arc for a certain arborescence? Well, the decisive point is if the tail of that arc here is spanned by the arborescence. Or in other words, because I have reachability arborescences, if the tail of the arc is reachable from the corresponding root. And then I will, therefore I will make the arcs in that way. So for example, say this arc here, its tail is that vertex. And this vertex is reachable from these two roots. Therefore, this is the vertex, the artificial vertex that corresponds to that arc. And I will make an arc from the two corresponding roots here. Now, what I'm actually searching for is right now an arborescence packing in that new digraph here that spans all the vertices in C. That's what I need to merge. Now, when I'm saying in general, I want an arborescence packing that spans all the vertices in C, this is not that easy to achieve. If you give me in general just a subset of the vertices and tell me you want that to be spanned, can I find such arborescences? This is a problem called Steiner arborescences. And this is NP hard even for only two arborescences. So that doesn't work. But right now, here I am in the very lucky situation that every of these artificial vertices I have created here have only one out neighbor. So what I can do, I can just add sufficiently many vertices that come from that only out neighbor that go back to the artificial vertex. Arcs, I mean. I can add sufficiently many arcs that come back from the vertex to the artificial vertex. And for that to work, it is very decisive that actually these artificial vertices have only one out neighbor, because otherwise I might create roots, I might create arborescences that walk back from C into an artificial vertex and go out again. And that would destroy my whole picture. That would not be, I would not be able to merge that afterwards. But right now, once an arborescence enters an artificial vertex going away from C, well, it can't go back because there's only one single out neighbor and it's been there already. That's where it came from. So that won't happen. And now I know if I have a set of arborescences, where do I not use the red arcs? Then I span everybody in C. Well, then I just have sufficiently many arcs I can use to span the remaining artificial vertices as well. Okay. So that's already a short explanation for the algorithmic sense, but now I will also show you how to actually prove this. So now I need to prove that in this graph on the right, in D prime, I can apply Edmonds' strong theorem. So I need to show that the condition is satisfied in this rooted digraph, D prime. So what I need to show is I need to take some arbitrary subset of V prime union R prime that is not only in R prime, and I need to show that is in degree is sufficiently high. That's the condition for Edmonds' strong theorem. Okay. Now how do I do that? Well, the only thing I have is that the original graph D satisfies the condition of the theorem of Kamiyama, Kato, and Takizawa. So that I need to use in some way. Now I have to set X, and the first thing I can observe is that I may very well assume that X intersection C is empty, is not empty. Because if it is, I can pick some vertex in X minus R prime. I have supposed that X minus R prime is non-empty. And I have just put sufficiently many arcs coming into that vertex. So that set would already have its in-degree sufficiently high. So I may very well assume that X contains at least one vertex of C. Okay. And now I need to define a set in D that corresponds to X. And from whose in-degree in D, I can conclude a big in-degree of X in D prime. Okay, so firstly, I look at all the vertices in D, and I say, which are not in C, and I say, are you reachable from any root that's not an X? And if they are reachable from any root that's not an X, I will not put them in that set. And if they're not reachable from any root that's an X, I will put them in that set. That I call U. So, for example, here, the only root that is not an X is that one here on the right. Oh, oops, is that one here on the right. And these three vertices here are the vertices in V minus C, which are not reachable from this root. And actually, there should be V union R minus C. Yeah, there should be V union R minus C. That's a typo. These are the vertices which are not reachable from this one root. So that is U. And what we can already see is that U certainly has no incoming arcs. Because, let's follow from this definition. I cannot have an arc whose tail is reachable from one of the bad roots and whose arc is not, whose head is not, just because there is this arc. So if the tail is reachable, so is the head. Okay. And now what I will do, how I will create my set I make reference to, is that I will add X intersection C. So C exists in both graphs, there is no problem. So I can also have X intersection C in the graph D. And I can add this. And this gives me my set Y. So I started off with the set X, then create my set Y. Now I want to conclude a high in degree of X by the high in degree of Y. So I want to show that the in degree of X is at least the in degree of Y. And the way I will do this is that I want to look at every arc that enters Y, and I want to say there is a corresponding arc entering X. So basically, I want to find an injection from the arcs entering Y to the arcs entering X. And once I have that, I have proven that the number of arcs entering X is at least as big as the number of arcs entering Y. Okay. So let's take an arc that enters Y. Well, what can I say about V? As I told you before, U, the smaller set, certainly had no incoming arcs. So, well, the only possibility for V is left to be in the upper part, to be in X intersection C, right? U has no incoming arcs. The only possibility left is in C. Now, where could U live? Well, first, U could also be in C. So it could look like that. Well, in that case, exactly the same arc also exists in X, in D prime, I mean, and it also enters X. Okay, So maybe the more interesting case, what happens if U is not in C? Okay, U is not in C. What does that tell me? This tells me U is reachable from some vertex in R prime minus X. Because that is the definition of that's the definition of Y, of the set U I defined before. So U is reachable from some R. And of course, also UV is an arc entering C. So I know that in this graph D prime, I have created that vertex TOV. Because UV is an arc entering C. Well, and because U was reachable from that vertex R, I have also created that arc. And by definition, I have also created that arc TOVV. Now, I don't know if my artificial vertex I have created is an X. But what I do now is that this vertex in R is not an X. And then I have a path of length 2, and then I end in X. And then one of these two arcs has to enter X. Because the first vertex is not an X. The second vertex, I don't know. But the third vertex is an X. And so one of the two arcs has to enter X. Okay. And both of these arcs contain that vertex TOV. So this is indeed an injection. Every arc I take entering Y, I will find exactly one arc entering X. Okay. That basically finishes the proof. Because now I know for every arc entering X, excuse me, the other way around. For every arc entering Y, there is an arc entering X. So the number of arcs entering X is at least as big as the number of arcs entering Y. Okay. So what does it give me? I know the number of arcs entering X is at least the number of arcs entering Y. And then I get this term here. So that is the condition I had in the theorem I'm proving. The theorem of Kamiyama, Kato, and Takisawa. But what's PDY? Well, Y contains a part of C, and certainly nobody that does not enter C in any way. So PDY is exactly the set of roots that can see C, and that is R prime. The set of roots I have in D prime. And also by construction, Y intersection R is the same as X intersection R prime. So I get this integration, and this yields me that I can apply the theorem of Edmonds-Strong theorem. Well, I have this graph, and now I get my arborescence packing of arborescences that start in R prime and span all the vertices in V prime. Okay, so now I have that. And also I recall you, I had the reachability arborescences for when I had deleted C in the very beginning. What I can do now is I can merge those. I look at the whole graph. I keep the arborescences I had in D minus C. I take the arcs entering C in the same color, and I take all the arcs in C in the same color. And all those arcs I created, which leave C in D prime, I just discard them. And what I'm left with is actually a packing of reachability arborescences in D. So that's the end of the proof. Okay. So that was basically now the inductive proof of the theorem of Kamiyama, Kato, and Takezawa, which uses nothing but Edmonds' strong theorem. Okay. What I want to show you for the rest of the talk is how to extend that approach to somewhat more general settings. So first thing I want to talk about are Matroid-based packings. So far, I always required arborescences to span everything, either everything or everything they could reach. So now I am a slightly different setting. I say, first, what I'm looking at is Matroid-rooted graphs. And what that is I take a rooted graph as I had it before, where V and R are separate. And now I additionally do define a matroid on that root set. And what that gives me, now what do I want from my packing? What I want from my packing is that for every vertex, the arborescences, which it is contained in, form a root of that matroid. So I look at a vertex, I say, which arborescences do contain me? What are their roots? And these roots, I want to form a matroid, basis of the matroid, which is given. Okay. And that has been studied by my supervisor and two of his earlier PhD students, and was published in 2013. And again, they managed to prove a very natural condition is necessary and sufficient. So I can explain to you again why this condition is necessary. Say, I now have a subset X union R. I pick a vertex in there. How many arborescences need to see that vertex? Well, rank of the basis many. Rank of the matroid many. Because the basis has got to come in. Well, how many can come from inside the set? Well, a lot of arborescences can start inside the set, but on the other hand, the set getting to that vertex still has to be independent. So I can count on at most rank of X intersection R arborescences that come from the inside of the set. And all the rest has to enter. So again, I can see this condition is necessary. Proving that sufficient is, of course, more complicated. And now, what I want to next is I want to generalize in a way that I combine the matroid setting I just showed you with the reachability part. And this is a very natural definition, which is a Matroid-reachability-based arborescence packing. Now I'm saying, well, maybe again, not all vertices are reachable from all roots. And now I look at every vertex and say, I'm looking at all the roots that can reach this vertex. And among those, a matroid basis of this set should reach the vertex in the arborescence packing. So I'm a vertex in V. I have a certain set of arborescences that can reach me. They are part of the matroid. And the arborescences that actually do reach me in the arborescence packing shall be a basis of that set. And when I speak about a basis of a set in a matroid, I just mean a maximal independent set, a maximal independent subset of that set, or equivalently speaking, a basis of the matroid that arises from restricting to that set. Okay. And again, there's a theorem which was proved by Kirai in 2016, which gives a necessary and sufficient condition for this for such a packing to exist. And again, the necessity can be seen pretty simply by just the same argument as I just gave you for the other theorem. And what our method allows is to also conclude that theorem from the same theorem we had before. So we take the theorem on the first slide on just Matroid-based packings, which was from Duron-de-Chevigné and Nguyen and Szigeti. And one little thing we need to take care of is that that theorem dealt with simply matroid-rooted graphs. Meaning I had only one arc coming out of every vertex. So basically that theorem plays the role of Edmonds' basic theorem I showed you at the beginning. But in order to use it, we need something that rather corresponds to Edmonds' strong theorem in the matroid setting. But actually, the matroid setting allows to pretty simply conclude this stronger theorem from the weaker form. So in the basic setting, it's much harder to conclude the strong theorem. In fact, you don't conclude it at all from the basic theorem. You give an independent proof. And here you can pretty easily conclude the strong theorem from the basic theorem. And we do that. And afterwards we are able to apply a pretty similar proof technique to what I showed you before. So now we have that matroid setting. This means things get slightly more technical. I need to take a bit of care of what is spanned by what and so on. But basically it follows the same ideas and it allows to conclude the theorem of Kirai from the theorem of Duron-de-Chevigné and Nguyen and Szigeti. Okay. That was that. And what I still want to show you is how I can even further generalize this. And well, so far we've always been looking at digraphs. But people also started looking at things like mixed graphs and typographs, directed hypergraphs. And you can combine all of these concepts. And I will not give you the definition for mixed graphs and typographs in detail. I will give you right away the definition of a mixed hypergraph, so the combination of both. So a mixed hypergraph consists of some vertex set, and then it has hyperedges and diperedges. So a hyperedge is basically just a subset of the vertices of arbitrary size. And for our purposes, its size is always at least 2. And the diperedge basically is an arc that has a lot of tails, but just one single head. So that's a diperedge. And now, what do I want? I want to find arborescences in those mixed hypergraphs. And what do I mean by a mixed hyperarborescence? This is what I call a mixed hyperarborescence, is an arborescence in the mixed hypergraph. And mixed hyperarborescence is a graph that I can trim to become an arborescence. What do I mean by trimming? Well, there's 2 different operations for hyperedges and for diperedges. For a hyperedge, I will just choose 2 vertices in that hyperedge And I will choose a direction between the two of them, and I will make an arc like that. For diaper edge, I always keep that head, and I choose one of the tails. And then I get an arc like that. Okay. And now basically I have an arborescence. And with that definition of mixed hyperarborescences, I can define all the properties I had before in mixed hypergraphs. So I say the packing of hyperarborescences has a certain property if I can trim them so that the packing of arborescences I obtain has that property. What is very important here is that I first do the trimming and then I want to have the property. So basically, when I, for example, when I say I want to have a spanning packing, I do not look at a certain vertex, trim the arborescences though that they are spanning for that vertex, then look at a different vertex and trim in a different way so that I'm spanning again. I do not do that. What I do is I look at my packing, I first trim, and then what comes out of that has to be spanning for everybody. Or in the same way, reachability packing, a Matroid-reachability packing, or whatever. Okay. Yeah. And for the definition of mixed graphs and hypergraphs, well, you can guess them. For mixed graphs, I just know that every hyper edge is of size 2, every diaper edge has only one tail. And for diapergraphs, I have no hyper edges. So basically, now I have four things I may want to have in my packing: reachability, Matroid-based, mixed graphs, and diapergraphs, and I can combine all 4 of them in arbitrary ways. So that gives me basically that table here. I can just start from the basic case, and then I can add whatever I want. So now I will make a little survey about all these combinations. And every paper that is listed here has deserved that by providing both a theorem, a characterization of these graphs, and a polynomial time algorithm with it. Okay, so the basic case, that's what we started from. That was proven by Edmonds. Then there's this reachability case. That's the theory I showed you before. And that's actually the proof I showed you, the proof that I showed you in detail before. How to get the reachability from the basic case, or that's a little lie, from this stronger version. Okay, then all these things have been considered. Mixed graphs were considered by Frank. This is also pretty old already. The Matroid setting, that's the theorem of Durand-de-Chavigny in 2013. Unfortunately, in this table, a lot of co-authors have fallen prey to the lack of space, so my apologies to them. Yeah, for typographs, this was also proved by Frank with some co-authors. And so these were the 4 basic things. When I have just one of the 4 properties, I can do all of that. And now people started wondering whether they could be combined. There is this theorem that combines reachability and typographs. This was by Berchi and Frank in 2008. What I found pretty astonishing in the beginning is that this generalization of the reachability theorem appeared actually before the reachability theorem. But apparently the theorem of Kamiyama, it was in a pretty slow journal, and theorem of Berchi and Frank was a conference paper, so it just appeared way faster, and in fact everything went in the correct way. Apparently there's also a somewhat older journal version of the theorem of Kamiyama. Okay. Then there's this theorem on reachability and matroids. This is what I showed you a second ago, proven by Kirai, and yeah. As I showed you before, we can reprove this by a conclusion from the Matroid-based setting. Okay. Then there was another article from a group in Grenoble that covered quite a lot of cases here. So basically, they proved the two theorems in the second row, and all the rest just followed as corollaries. So they covered a lot of cases, and that was also the first time they started surveying all these different things. And I think they have a very similar table to that one in their paper. Then what proved to be somewhat harder is the point where you have to combine reachability with mixed graphs. And this was then proven by Matsuoka and Tanigawa in 2019. And actually these characterizations start becoming a little more ugly once you have to combine reachability and mixed graphs. So all these characterizations have to use bisets, if you know what that is, but I don't know if you know what bisets are, but if you don't, it's just somewhat more complicated. And this is actually also the first article where they started applying inductive ideas, meaning they deleted a strongly connected component and then applied induction. But for dealing with a strongly connected component, they did not define an auxiliary graph, but they supplied some submodular optimization to deal with that strongly connected component they had deleted. Okay. And then next article is pretty recent. I think it's also not yet published. It appeared on an archive in March. And it was proven by Gao and Yang, who managed to extend the theorem of Matsuoka and Tanigawa to the Matroid setting. Yeah, and actually we do believe that the proof technique of Gao and Yang would also allow to completely complete this table. So when reading through the article, we believe that there's no issue if you use mixed hypergraphs instead of mixed graphs. But okay, they didn't do it. And so last theorem we have in our article remains at least somewhat new. We managed to complete this table and reduce the theorem for the very top case from the theorem of mixed graphs, a theorem that combines everything but reachability. And again, we go in a very similar fashion as before. We prove a stronger version with that Matroid idea, which I mentioned before. And then we apply a proof technique similar to the one I showed you for concluding the theorem of Kamiyama. Okay. And of course, the last open case without Matroid just follows by applying the theorem there to the free Matroid. Okay. Yeah, and all of these proofs are algorithmic. All of these theorems are proof of these theorems are algorithmic. Of course, in the Matroid case, you need to be provided with a Matroid oracle. So I'll conclude here. What we have obtained is a new proof technique that allows to add a reachability in several of these settings. Okay. It allows to conclude the theorem of Kamiyama, Kato, and Takizawa from Edmonds. This is still called the branching theorem, but this is Edmonds' strong theorem. In the original version, it was called the branching theorem because he starts basically in a setting with several roots for each arborescence. But this is Edmonds' strong theorem that I mentioned before. In the same way, as I showed you, we conclude the theorem of Kirai from the theorem of Durand de Javigny, Nguyen, and Szigeti. And we managed to complete this table I just showed you. And all proofs are algorithmic. So basically, of course, what our reductions do, they keep the algorithmic aspect once we're given a black box for the case without reachability. But this is always provided by the other articles. So indeed, we have algorithms to find these arborescences. What remains as a little open question is, can we find weighted algorithms? Meaning I give you a weight function on the arc set, And now I want to find my arborescence packing or mixed type arborescence packing or whatever in a way such that the total weight of the arcs used is minimal. And there are some ideas to attack this. Many of them work with weighted matroid intersection. And this is the current state of the art. And there are still, so the squares which are marked in red, they are known, and the rest are not. And of course, there are still quite some open cases. In particular, of course, the very top case would be interesting if one could solve this. But what also all proofs also gives you, it goes actually well with weighted packings. So once someone gives us an algorithm for the case of mixed graphs, matroid typographs without reachability, once we have a weighted algorithm for that, we can also give you a weighted algorithm for the very top case. Adding reachability won't destroy that. Okay, so that's it. Thank you.
Right, let's unmute and give the speaker a hand. Maybe.
Thank you.
Any questions?
So Datching's paper doesn't use weighted trees?
No, it uses mixed graphs, and it uses theorems that actually say that certain orientations exist. That you can orient the arcs in a way that afterwards have satisfied the condition to find your packings. I think these theorems will only give you some orientation that does the job. Afterwards, you can find some arborescences, but you do not know if in a different orientation that would also do the job. You could find better arborescences.
Okay.
So if there are no more questions, then yeah, let's thank the speaker again.
Thank you.
So first of all, I would like to thank Ben for letting me know that Florian has some interesting results to present. So in case you know someone whose work fits the theme of this reading group, then yeah, it would be great to hear their talks. Before we end, next week, Nishad will be giving a talk. So I hope to see you guys next week. I'll circulate the abstract soon. Yeah. Right. Yeah.
Oh, that reduction is really natural. Why would they use some weird sub-object?